The next example here, or the theorem here, is that it states that the multiplicity of roots of an irreducible polynomial over any field. If that is the case, what could be said about the multiplicity of roots, right, for any irreducible polynomial which is defined over any field? So that is the question that we are going to answer in this using this theorem. So here, suppose they are saying f of x is given to be an irreducible polynomial over f, then all of its roots have the same multiplicity. So this is a quite important result. It says that all roots, they would have same multiplicity if the given polynomial is an irreducible polynomial. So for that, what we do, we have this field as f. This is f that is given to us, and we have this closure of f. So by closure means this is an algebraic extension, and all the roots of this polynomial would be present here in f closure. So in this f closure, we assume that alpha and beta, they are the two roots of this particular polynomial f of x, and the multiplicity of first root alpha, that is given to be k, and the multiplicity of second root beta, that is given to be k dash. This we have assumed by ourselves. So next we are to prove that all the roots, they have the multiplicity as the same multiplicity. So that means we will prove that for the same multiplicity, this k should be equivalent to this k dash. So this is what we are intended to prove here. So for that, what we are doing, we know if you have some field here f, and if you have some polynomial here in fx only, and if you know its root is alpha, so that means you will have an field here f of alpha, such that you adjoin the root of this particular polynomial here to s. So this would be an extension field of this one, and you know if this is the irreducible polynomial corresponding to which alpha is a root, so you can write this f of x as the maximal ideal. This would be the maximal ideal, and when you have the quotient field corresponding to this maximal polynomial, this would act as a field which would be isomorphic to the field where the element alpha and the element beta have been adjoined to it. So using these two relations, you can also write this f of alpha is isomorphic to f of x divided by the maximal ideal, and then because this thing is same as this thing, so you also have this isomorphic to f of beta. So we have this particular relationship. So next, from here you can say that if you have some polynomial g of alpha here, so we can say if we have some polynomial, say g of alpha here, this one, so you could associate this polynomial g of alpha to some other polynomial g of x plus the maximal ideal, which is an element of this kind, right? And this is further isomorphic to this, so this will map to some element g of beta. So using this transitivity, so we can directly say that the polynomial g of alpha will map to g of beta, because these two fields f of alpha and f of beta, they are isomorphic to each other using this particular relationship. So accordingly, we can say if this is the given polynomial g of alpha, that means a naught a1 alpha plus up to a n alpha raised to power n. So this would be isomorphic to this one. So what would be g of x? In place of alpha, you will be writing x here, right? And this is added to this maximal ideal, and then this thing is mapped to g of beta. G of beta would be the same polynomial where x now has been replaced with beta. So this is the mapping that we got, and we know that this is an isomorphism. So we name this mapping as sigma. So we say sigma is an isomorphism. So by what do you mean by an isomorphism? A mapping which is 1-1, a mapping which is onto, and a mapping which is homomorphism is a isomorphism. So here it is 1-1 and onto, so that means because it is onto, so you can write sigma of alpha is equal to beta, right? So you can also look at this field diagram. So we have just said that sigma act as an isomorphism between f alpha to f beta, where this alpha and beta are the roots of the polynomial f of x, and we have adjoined it to the lower field f. So this is one mapping. So now next we have considered the closure of f. So we have this situation, we have f, we have f of alpha, and f of the closure of f would be above all. We have another situation, f, its extension field would be f of beta, and we have the closure of this f of beta. So this closure is nothing but this f closure, because f closure will contain all the elements and all the roots, so does this f of beta. So according to this diagram, we have f dash as the extension field of f, f bar as the extension field of f alpha, and f beta bar, that is the closure of this f of beta. So now this mapping sigma, this could be extended to another mapping sigma star from f closure to f beta closure, which we have defined by this, and this is also an isomorphism between these two. So f of the closure of f and the closure of f beta. And what is the closure of f beta? It is equivalent to f the closure of f only, right? So now you see this mapping sigma star from f closure to f beta closure, that is nothing but f closure. So we can say we have a mapping which is an isomorphism from the same field to the same field. So this is an automorphism. Automorphism is nothing but the isomorphism which is mapped from the same field to the same field. So according to this property, every automorphism induces a ring homomorphism. So sigma star will also induce a ring homomorphism. So we will call that ring homomorphism to be eta. So this eta would define a mapping from fx closure to fx closure, which is given by eta applying on some polynomial here having degree r to another polynomial here having degree r, whose members are a naught, the coefficients are sigma star a naught, sigma star a1, and so on. Why this is so? Because if you see what is sigma star was an automorphism. So every element here a naught, that would be equivalent to sigma star a naught, a1, that would be equivalent to sigma star a1, and so on. Sigma and the last element say AR, that is equivalent to sigma star AR. So this act as a homomorphism, and it preserves the structure for this mapping eta. So now because all of the three mappings, sigma, sigma star and eta, they are all the field homomorphism. First two being isomorphisms are homomorphisms, and third one is field homomorphism. So they all are field homomorphisms, so therefore they will act as identity. So now if they will act as identity, so I can write eta of f of x to be f of x only, because it acts as identity. So if I write this to be, in place of fx, I can write this to be f minus alpha raised to power k, because sigma of alpha is equal to beta. So I can write this quantity eta of x minus alpha raised to power k is equal to x minus beta raised to power k. According to this identity property, what would be sigma of x minus alpha raised to power k? This is nothing but it is equivalent to this x minus alpha raised to power k. So this quantity here and this quantity comes here. So from here you can say that because alpha was the root for this irreducible polynomial f of x that we have assumed in the very starting, which was occurring k times. So now because this is equivalent to this quantity, therefore x minus beta would also be a factor for this particular polynomial, and from here, from looking at this power, its power is k. So it is a factor which is occurring k times in the expression for f of x. So that means from here we can say that k is less than equal to k dash. Why? Because the multiplicity of the polynomial beta was k dash, and now we have written f of x as the factor x minus beta raised to power k into something something something. So from here you can say because the it was occurring k dash times, so k dash would be greater than this particular k. So from here we can state that k is less than equal to k dash. So if this is the case, so let us call it as equation number 1. So now if we prove that k dash is less than equal to k, so from these two expressions they too become equal, right? So the only possibility remains would be to prove this thing, k dash is less than equal to k. Now if you reverse this roles of alpha and beta from this very starting, from the one where we have said that f of alpha is isomorphic to f of beta, if you now say f of beta is isomorphic to f of alpha, so from here we can say that moving like this, so we can say that now if we interchange the role of alpha and beta, we can say that k dash is less than equal to k. So this is the second expression that we were seeking. So from this equation number 1 and equation number 2, we can state that this k is equivalent to k dash. So proving that the multiplicity of all the roots, we have assumed only the roots alpha and beta, the multiplicity was, its multiplicity was k, its multiplicity was k dash. Now we have proved that their multiplicities are same, so that means all the roots of this polynomial f of x, they have the same multiplicity because the roots alpha and the root beta, they were chosen arbitrarily. So this result is valid for every other root as well. So we have a corollary corresponding to this particular result saying if f of x is any irreducible polynomial over f, then we can write this polynomial f of x as the product of x minus alpha i's, where what is this alpha I? They are the roots of this polynomial in the splitting field. So that means we have how many roots? We have r such roots available for this polynomial f of x, and the multiplicity of each root would be k. So k represents the multiplicity of each root. So that means we are saying that every root has the same multiplicity. So that this clearly follows from the theorem that we have just taken. So let us see the proof very quickly. So suppose f of x is the irreducible polynomial over f, and if alpha 1, alpha 2 up to alpha r, they represents the root of this polynomial f of x. So we assume if alpha 1 has the multiplicity k, so according to previous result, all the roots alpha 2, alpha 3 up to alpha r, they would have the multiplicity k as well, because this is given by the last result. So we can write this polynomial f of x as a times the factor x minus alpha 1 raised to power k, another factor x minus alpha 2 raised to power k, and so on x minus alpha r raised to power k. So our polynomial here becomes f of x is equal to this pi I varies from 1 to r, x minus alpha I raised to power k. So I hope this is clear to you all.